All right, let's dive in. Have you ever had this happen? You press a ceramic part, a tile, maybe a substrate, and it looks absolutely perfect, flawless. But then it comes out of the kiln, and it's warped, it's cracked, it's a total mess. It's a super frustrating mystery, and today we're going to solve it. Okay, check this out. On the left, you see what we call a green part. That's just the term for a part that's been pressed but hasn't been fired yet. And it looks great, right? Straight walls, nice sharp corners. But then you look at the right. What a disaster. After firing, it's bowed into this weird hourglass shape, and you can see cracks starting to form. So what on earth happened inside that kiln? I mean, that's the big question here. But here's the secret. The defect wasn't created in the fire. It was just revealed by the fire. The real problem was an invisible flaw, a hidden weakness, that was baked in from the very moment the part was pressed. And the name of this invisible culprit, this ghost in the machine, is green density. This concept is absolutely the key to understanding why so many parts that look perfectly fine end up failing. So what is it, really? Well, simply put, green density is just a measure of how tightly packed all those little ceramic powder particles are before you fire them. Think of it like the foundation of a house. If you get a good, uniform green density, you're setting yourself up for success. But if it's poor or non-uniform, you're pretty much guaranteeing failure down the line. This slide right here just says it all, doesn't it? On the left, you see what happens when your green density is nice and even. When you fire it, the whole part shrinks uniformly. Yeah, it gets smaller, but it keeps its perfect shape. Now look to the right. This is what happens when you have uneven density. Some areas are packed tighter than others. So in the kiln, those less dense spots shrink way more, and they end up pulling and twisting the whole part into that distorted mess. And that brings us to the most important rule in this whole game. The fired part is a memory of its green state. You gotta remember, the kiln isn't a magical place. It's a place of truth. It will faithfully and sometimes brutally reveal every single flaw that you pressed into that part from the very beginning. So if that green state is so incredibly critical, how do these invisible density problems even get created? To figure that out, we have to go look inside the press itself. What we're looking at here is a classic industrial die press. The process seems simple enough, right? You fill a cavity, the die, with ceramic powder, and a big punch comes down with a ton of force to pack it all together. But it's right here, in this moment of intense pressure, that things can start to go wrong. The two main troublemakers are die wall friction and uneven pressure. See, as that punch comes down, all the powder particles are trying to shift and rearrange themselves. But the particles right up against the metal wall of the die, they get dragged down by friction. That means the powder in the middle of the part gets packed way tighter than the powder along the edges. And this is why how you apply the pressure matters a lot. With single-end pressing, where only the top punch moves, you get the most pressure at the top and the least at the bottom. That creates a huge density difference. The much better way to do it is double-end pressing, where both the top and bottom punches move in. You're basically sandwiching the powder, which spreads the pressure out way more evenly and seriously cuts down on those density problems. Okay, so knowing what causes the problem is half the battle. Now let's get into how engineers can actually take control of this process and fight back against those invisible flaws. A good process engineer has a whole dashboard of levers they can pull. You've got the pressure itself, the speed of the press, how much moisture is in the powder, even the kind of binder you mix in. Every single one of these things has a direct impact on that final green density and how uniform it is. So let's take the most obvious one, pressure. This graph shows a pretty classic relationship. As you crank up the compaction pressure, the green density goes up. You're just forcing the particles closer together. But you can see how the line starts to level off, right? At a certain point, adding more and more pressure just gives you diminishing returns. And why do we care so much about getting that higher green density? Well, this graph explains it perfectly. They have an inverse relationship. The higher your green density is to start, the less the part has to shrink in the kiln. And less shrinkage means better control over your final dimensions, less internal stress, and a much lower chance of warping or cracking. It's a huge deal. But look, even with the best controls, things can still go sideways. So how do you find a problem before you fired 1,000 bad parts? You have to become a kind of materials detective and learn how to read the green state. Honestly, the best technique is to just get your hands on it. You take a couple of sample parts right off the press line and you break them on purpose. The way a green part fractures tells you a story. If it's a clean, uniform break, that's a good sign. But if it looks layered or fleeky, that can tell you you've got lamination from trapped air. And here it is, the ultimate field guide for our detective work. This chart is your cheat sheet. It links all the common pressing defects directly to what's causing them and how you might fix them. See that hourglassing from our very first slide? Primary cause, pressure gradients. The fix? Use a double-end press. Or what about lamination? That's usually trapped air. A quick fix for that is to bump the press. That's a short release of pressure in the middle of the cycle that lets the air escape. But what if you're making something really complex or supercritical? Think like a turbine blade or a medical implant, where even the tiniest variation in density is a total deal breaker. For parts like that, you have to go beyond the standard die press. And this is where things get really cool. It's called isostatic pressing. Instead of a hard metal die, you put the powder into a flexible, rubber-like mold. Then, you put that mold into a fluid, and you pressurize the fluid. This gives you perfectly uniform pressure from every single direction at once, completely getting rid of die wall friction. It is the absolute best way to get a uniform green density. And that brings us right back to where we started. All the flaws and all the triumphs of a finished ceramic piece are really just echoes of how it was created. So the next time you see a tile or any ceramic part, remember that hidden story locked inside. Remember that the fired part is a memory of its green state. And ask yourself, what is your process remembering?